Um, our second speaker of the day is Nima Hoda from the École Normale Supérieure, who will talk about constructing bisimplices.
Okay, yeah, thanks a lot for the invitation to speak. So yeah, I'm going to talk about this family of cells that I constructed, which are kind of bipartite analog of simplices. There's not much, or I guess there's not anything in my talk that's really related to polyhedral products, but the talk is about using combinatorial means to construct this family of cells, construct cell complexes that do give classifying spaces for certain classes of groups. So I think some in spirit, it's it's connected to the topic of the conference. So right, so talks in three parts. I'll sort of give this motivation of the classifying space, and then I'll talk about some of the tools that are used to construct these cells, which are mostly discrete Morse theory of Forman, and then I'll go on to state and prove a sphere recognition theorem that's used to prove that the construction is valid. Okay, so in terms of the motivation, let me just mention that there's a family of square complexes called quadratic complexes. They're simply connected. They satisfy a certain local combinatorial non-positive curvature condition. They include cat-0 square complexes, but they're more general. In some ways, or in many ways, they're analogous to systolic complexes. And they're sort of things that are nice to have your group acting on, like systolic complexes, like cat-0 cube complexes. And I studied these things during my graduate studies, and but they're not contractible, and I wanted to make them contractible, and I had the feeling that if I could plug a cell wherever there's a complete bipartite subgraph, that I would get something that's contractible. And that turned out to be the case, but it wound up taking a lot of effort to actually construct these cells. So the motivating application for me was this following theorem, that if you span a bisimplex on each kn plus 1 n plus 1 subgraph with m and n at least 1 of a locally finite quadratic complex, you get a contractible complex with the same two skeleton. Okay, so how do you go about constructing a family of cells that are analogous to simplices, but where the one skeleta are all complete bipartite subgraphs rather than complete subgraphs? So for K22, we already have squares. They seem they seem like the right thing. They were for my application. So we could start by the next least complex complete bipartite graph is K23. So we could start by spanning a square on each of the K22 subgraphs. That so that's three squares here. We have two in the front and one sort of in the back if you will. And that gives us two-dimensional sphere. We plug that sphere with a three-dimensional cell, and there we go. That's our 1-2 bisimplex. And we can sort of continue this idea inductively and define bisimplices in the following way. So a 1-1 bisimplex is a square with its usual cell structure. An mn bisimplex with m and n at least 1 is obtained from the complete bipartite graph kn plus 1 n plus 1 by first spanning a single m prime n prime bisimplex on each proper k m prime plus 1 n prime plus 1 subgraph with m prime and n prime at least 1. We have access to those lesser bisimplices inductively, and once we expand those lesser bisimplices on the proper subgraphs and made the correct identifications along common faces, we call that the boundary of the bisimplex. And then we take the resulting m plus n minus 1 sphere and plug it with an n plus n cell. So that's, you know, that's an idea for a construction. In particular, what you get is, you know, an mn bisimplex is a cellulated ball of dimension n plus n, such that the one skeleton is an n plus 1 complete bipartite graph, or complete bipartite graph on parts of size n plus 1 and n plus 1. And there's exactly one higher cell for each complete bipartite subgraph on parts of size at least 2. And that cell is a bisimplex with the appropriate indices. And that's sort of, you know, it says, I wrote in particular there, but I think that roughly will uniquely determine what bisimplices are, because you know, any regular cell complex is fully determined by its poset of cells with the inclusion relation. And this, you can sort of read off what that poset is from this little, from these points here. And we can compare that with simplices. So an n-simplex is a cellulated n-ball whose one skeleton is the complete graph on n plus 1 vertices, and which has exactly one simplex for each complete subgraph. Okay, but there's a big, huge problem with this definition, which is that the inductive step, you know, crucially depends on this boundary of the bisimplex being homeomorphic to a sphere, sphere of dimension n plus n minus 1. So the only way this definition makes sense to actually define cells is if we can prove in that inductive step that this is actually a sphere, and that's going to be how we're going to spend the rest of this talk, is proving that's a sphere, developing the tools that we need to do that. So the primary tool that we're going to use for that purpose is Forman discrete Morse theory, and Forman's sphere theorem, which is going to tell us when something is homotopy equivalent to a sphere. But first, let's just mention some terminology. When I say cell complex in this talk, I mean a regular CW complex. CW complex is regular if its attaching maps are all embeddings. So the loop or the graph with one vertex and one edge is not a regular CW complex, but a multi-edge, as shown here, is a regular CW complex. That's allowed. Okay, so I'm going to define a Forman discrete Morse matching, which is essentially like a Morse function, a discrete version of a Morse function. A Morse matching on a cell complex X is a collection of pairs of cells, which I write sigma I arrow tau I, such that sigma I is a codimension 1 face of tau I, and I'll denote that by sigma I less than tau I. And such that each cell appears in at most one pair. That's why it's called a matching. It's kind of like a matching on a graph. And there's also no cycle of the following form. So what we're seeing here is that sigma I1 is matched with tau I1, which has sigma I2 as a codimension 1 face. And sigma I2 is matched with tau I2, which has sigma I3 as a codimension 1 face, and so on, until eventually we're back to sigma I1. And that kind of cycle is forbidden. I'll just note that the sigmas, if sigma I1 has dimension D here, then all of the sigmas have dimension, all the sigma I's here have dimension D. And all of the taus have dimension D plus 1, right? So that just follows from property 1. And so any collection of pairs satisfying this property, these three properties, is a discrete Morse matching. A critical cell of a Morse matching is one that's not appearing in any pair. So just to make sure we understand that, let's look at some examples. We're starting with some non-examples. So the underlying cell complex here is just the triangle with its usual cell structure. The first example here is not a Morse matching because this vertex is matched with this is zero-dimensional cell is matched with a two-dimensional cell, so that's not a codimension 1 face. In the second example, we're violating the matching rule, rule number 2. Here we have a vertex that's matched to 2 different edges. This one's a little bit hard to see, but what it's supposed to be is that the 2 sloped edges of the triangle are both matched to the 2 cell, and that also violates the matching rule. And finally, here we're violating the no cycle rule. We have a vertex that's matched to an edge. And then this vertex is a codimension 1 face of that edge, and is also matched to this edge, and so on until we're back to our original vertex. Okay, so these are all the things that can go wrong. And here are a couple examples of actual Morse matchings. In this example, so this is a tree. The only critical cell is this this blue vertex over here. In this example, there are 3 critical cells. There's this bottom edge, and its 2 endpoints are also critical. Okay, so what do you get from Morse matching? What is it good for? So here are a few theorems of Forman. If the union of the relative interiors of the critical cells of X forms a subcomplex Y, then X collapses onto Y. So in this particular case, where the critical cells form a subcomplex. So I mean, the thing that you need is that if a cell is critical, then all the cells appearing on its boundary are also critical. So if you satisfy that property, then the Morse matching gives you a collapsing strategy onto the subcomplex of critical cells, and that's not so hard to see. You go to the top dimension where you see non-critical cells, and because of this no cycle condition, you can always you can define a partial order on those two top dimensions, and using this no cycle condition, you can always find an initial cell, and then it turns out that initial cell can be you can perform an elementary collapse on that initial cell. And then by induction, because you wind up with a simpler complex with which and the restriction of the Morse matching to that complex is still a Morse matching. The next theorem is more interesting. Says that okay, if n sub d is the number of critical cells of dimension d, then X is homotopy equivalent to a CW complex with n sub d cells of dimension d. Right, so here, you just have a Morse matching. There's no condition on the set of critical cells. And what happens here is you may not have a free cell to perform a collapse, but you can sort of internally collapse the cell, and any cells that happen to be attached to the cell that you're collapsing, their attaching maps can sort of follow the deformation retraction, and so you wind up with something that's homotopy equivalent, and you repeat this for all the matched pairs, and you wind up with something that has exactly as many cells as of dimension d as you had critical cells of dimension d for every d. Yeah. Of course, the result may not be a regular CW complex, but it'll be a CW complex. And as a kind of immediate consequence of this theorem, we have Forman's sphere theorem, which says that if X has two critical cells, sigma 1 and sigma 2, then first of all, one of those critical cells has to be of dimension 0, because if X is homotopy equivalent to a CW complex with two cells, well, any non-empty CW complex has at least one vertex. So one of the two cells has to be of dimension 0. And moreover, X is homotopy equivalent to a sphere of the dimension of the other critical cell, and that's essentially because any CW complex with two cells is a sphere. One of them has to be a 0 cell, and the other one is just has its boundary. The other one is either also a 0 cell, in which case you have a 0 sphere, or it's something that has non-empty boundary, which is and the boundary is just mapped to the first cell, to the first vertex. Okay, so that's nice. We're trying to prove that something is a sphere. Now we have a tool to at least prove that it's homotopy equivalent to a sphere. And here's an example. So we have here's the boundary of the 1-1 bisimplex that we constructed earlier. And so the Morse matching is described here. Just to be clear, you know, A, B, C, and D are matched to to edges. The edge AB is matched to the square ABED, and the edge BC is matched to the square BCDE. The only cells that aren't matched are the square ABCD and the vertex E. So those are the critical cells. So then by the Forman sphere theorem, we see that this complex is homotopy equivalent to S2. Of course, in this case, it's obvious. We can see that it's homeomorphic to S2. And it turns out that we can describe Morse matchings having exactly two critical cells for all of these boundaries of bisimplices in this inductive step. So yeah, so that's great. So we in this inductive step, you know, we can prove that we have at least a homotopy sphere, but we need to go a little bit further. We need to prove that it's actually homeomorphic to a sphere. And luckily, the generalized Poincare conjecture is a theorem. And it says that if a topological manifold is homotopy equivalent to a sphere, then it is homeomorphic to a sphere. But right, so if we can manage to prove that our inductive boundary of a bisimplex is a topological manifold, then we'll be done. But in order to do that, we need to start looking at the local topology, and we need to start talking about links, because that's how you study the local topology of cell complexes. And it starts to give an idea of an inductive process, because we want to prove this, that our complex is a sphere. We know, you know, we can show that it's a homotopy sphere, say, but then we need to prove that the links are spheres. Well, then maybe we can show that they're homotopy spheres, and then show that the links and links are homotopy spheres, and so on. Okay, so yeah, let's talk about what it means for you know, what it means to be able to take links in a cell complex. You know, we know how to do it in certain families of complexes, simplicial complexes, cubical complexes, but it turns out that it's not possible in general for all regular CW complexes. Okay, so here, yeah, so here's the main theorem that we're going to use and apply in this in our inductive step of the construction of bisimplices. Let X be, call it the sphere recognition theorem. Let X be a cell complex with links. That's in double quotes. We'll define that soon. If X has a Morse matching with two critical cells, and the link of every cell of X also has such a Morse matching, then X is homeomorphic to a sphere. This is, you know, this is kind of nice in view of the fact that in general, detecting whether a given complex or even simplicial complex is a sphere is an undecidable problem. And so here we have this family of spheres that are sort of easily recognized without too much computational complexity, even. Well, non-deterministic polynomial time, I think. Yeah, and it turns out that yeah, so we can apply this theorem in the case of bisimplices, because we can also show that that these in our inductive step we can show that boundaries of bisimplices do have links, and we'll talk a bit about more about that. So this is sort of all we need to complete our construction. So we're going to spend the rest of the talk just talking more about links, and then giving a proof of this theorem. Okay, so right. So let X be a cell complex, and let BS of X be the barycentric subdivision of X, viewed as a directed simplicial complex. What I mean by that is that the barycenters, the edges between barycenters are going to be directed from, excuse me, from the cell of higher dimension to the cell of lesser dimension. So that's a natural way to direct the edges. The BS link of a cell sigma, which we're going to denote BS link of sigma, is the full subcomplex of BS of X that's induced by the barycenters of all cells of X that contain sigma. So yeah, so just to make sense of that, let's take a look at it at a pair of simple examples. Here, what we have is the 2x2 grid of squares. That's sort of in black. We took the barycentric subdivision, so some new vertices and edges are introduced, and we're going to take the BS link of this central vertex here, sigma. So so we take all the barycenters of all the cells that contain sigma. So there are 8 such cells. There's the 4 squares, and then there's 4 edges. Taking the full subcomplex on all those barycenters, we get this sort of subdivided square as the BS link of sigma. In this example here, we started with 2 triangles. And we're going to take the BS link of sigma, which is the edge that's common to the 2 triangles. And so we take the barycentric subdivision. So those new edges and vertices are indicated in blue. There are just 2 cells that contain 2 original cells that contain sigma. There's the 2 triangles, and we take their 2 barycenters, and those are and the full subcomplex on those 2 is discrete. So in this case, the link is just two vertices. Okay, so that's what a BS link is. If it turns out that the BS link of sigma is the barycentric subdivision of some complex, of some cell complex Y, then we say that Y is the link of sigma, and we denote it by link sigma. If the link of sigma exists for every cell sigma of X, then we say that X has links. So if you're sort of wondering why we need this definition, isn't it always the case that the links exist? So the thing to be aware of is the existence of these things called homology spheres. So you have these things that are, you know, even in dimension 3, you have these topological triangulated, 3 manifolds that have the same homology as the 3 sphere, but which are not the homeomorphic, and of course don't have the same homotopy type as the 3 sphere. If you take the double suspension of such a thing, you'll wind up with something which is actually a sphere. And you could plug that sphere, that 5-dimensional sphere, with a 6-dimensional cell. And now, if you try to take the link of a certain edge, you would get something that's the original homology sphere, but it would want to be plugged by want to be plugged, and of course that's not a valid cell complex, because the boundary of a cell in a cell complex should be a sphere and not a homology sphere. So that's the sort of thing that can go wrong, and that's why we need this definition here. Okay, so right. So once we do have that, though, once we have a cell complex that has links, then things work out the way we sort of expect them to, from cubical complexes and simplicial complexes and polyhedral complexes. So right, polyhedral complexes, for example, always have links. Right, so if sigma is a D cell in a complex that has links, then the K minus D minus 1 cells of the link of sigma are in one-to-one correspondence with the K cells of X that contain sigma. So that's exactly, and in fact, it's a sort of, it's a natural bijection, because really it's the inclusion poset of the link of sigma is just sort of a restriction of the inclusion poset of X to the cells that contain sigma. So that all sort of works out the way you expect it to. Okay, so how do we ensure that that a cell complex has links? So as I sort of brought up in the discussion on homology spheres, sort of the issue is that the link of a cell is constructed out of cells corresponding to these higher dimensional cells, and you need those things to be actual proper cells. So what does that mean? So if I take a cell tau in the link of a cell sigma, then the boundary of tau is just the link of sigma in the boundary of rho, where rho is the cell corresponding to tau in the link of sigma. So let's take a look at this picture. Here we have sigma. It's contained in 2 maximal cells. So the link is comprised of 2 maximal cells. One of those cells is tau over here, which is coming from the cell rho, which contains sigma. And if we think about the boundary of tau, it corresponds to the link of sigma in the boundary of rho. And as long as that link So in particular, if X has links, then so should the boundary of every cell of X. And conversely, it turns out that if and moreover, the link of every cell in the boundary of a cell of X should be homeomorphic to a sphere, right? Because it's going to be the boundary of a cell in the link of sigma. And conversely, if you build a cell complex out of cells that satisfy this property, right? Out of cells where the boundary has links and all the links are homeomorphic to spheres, then your cell complex will have links. And this is the way that we ensure that boundary of the MN bisimplex in our inductive construction has links and are then able to apply the sphere recognition theorem. Okay, and moreover, we know that if a simplicial complex has spherical links, then it's homeomorphic to a topological manifold. Well, it's a fact that if X has links, then the links of simplices of the barycentric subdivision are actually joins of BS links and of barycentric subdivisions of boundaries of cells of X. So if all of those are spheres, right, if you take joins of spheres, you'll get spheres. If all of those are spheres, then the links of cells of BS of X are all going to be spherical. And so in that case, BS of X is a topological manifold. BS of X is homeomorphic to X, so X is a topological manifold. Okay, so those are all the sort of ideas that we need to put together, and so let's prove the sphere recognition theorem. Right. So so what we want to prove is that if X is a cell complex with links, if X has a Morse matching with two critical cells and the link of every cell of X also has such a Morse matching, then X is homeomorphic to a sphere. By the Forman sphere theorem, X is homotopy equivalent to a sphere, right? Because it has that kind of Morse matching. Now we're going to proceed by induction. If dimension of X is 0, then X is a discrete space, but it's also homotopy equivalent to a sphere, so it has to be homotopy equivalent to the 0 sphere, and so it has to be the 2-point space. Okay, so that's the base case. Now, if X has dimension D, which is greater than 0, we're gonna prove that X is a manifold, and then we'll be able to apply the generalized Poincare Conjecture. So what we're going to do is for an arbitrary cell sigma, we're going to show that the link of sigma is homeomorphic to a sphere, and then by that last fact, this will prove that X is a topological manifold. Let tau be a cell in the link of sigma, and let rho be the corresponding cell of X. Then the BS link of tau taken in the link of sigma is isomorphic to the BS link of rho. That's just by consideration of the restrictions of the cell post set. Sort of if you restrict in 2 steps, it's the same as restricting once. And so that tells you that if you take a link inside of a link, it's the same as just taking a link of a higher cell. And so the link of sigma has links also, so it satisfies that condition of the theorem statement. And it also has a Morse matching with 2 critical cells. That's by hypothesis. And its links also have Morse matchings with 2 critical cells by the previous sentence. So by induction, link of sigma is homeomorphic to a sphere, and X is a manifold, and we can apply the generalized Poincare conjecture to tell us that X is homeomorphic to a sphere. And yeah, that's the proof of the sphere recognition theorem. Yeah, I guess I'd like to stop there.
We should thank Nima